think we're all here. So we'll go ahead and get started. This is going to be, today we're going to basically do what we've been talking about in lecture, which is kind of nice. We're going to do 4 examples together, and then I'm going to turn you loose for 6. And then after you do your 6, then I'm going to come around and look at your work, and I will give you this sheet, one of these. This is actually, I decided to go ahead and make it due when you come to take your test after Thanksgiving. This is for lab credit, so this is your lab credit thingy. Now there's actually a Lewis structure assignment at the end of part 8, and that will just be regular homework assignment, okay? So I'm kind of changing it up from what I did with the nomenclature. Yeah, today's nomenclature lab is due, okay? Either like now or before, beat me to my, not now, but just today. Or beat me to my office before I get here on Friday, that sort of thing. So, all right, so these are the steps we've been talking about. Now, in your lab handout, you have kind of these grid things. You should have some sheets, I think 6 or so. So go ahead and find, yeah, exactly. Go ahead and find the sheet thing. And actually, each one that we do, I'm going to ask you to go ahead and fill it out, okay? So it looks like this. The first one that we're going to do, oh yeah, before I do that, at the bottom of the column, these actually, mine go across, but yours go down. So you'll have to kind of, what do they call that in math? They call that something. So anyway, at the bottom there are some checks, and we'll be doing each one of these checks too. So that should work out fine. Let's see, how do I go to the next one? Oh, that isn't what I wanted. Okay. All right, back up. So the first one we're going to do is, let's see, how do I go to the, I guess I just got to let it run, but I think I can speed it up by, okay. Whatever. Okay. Are you serious? Okay. So the first one we're going to do is NH3. Okay, so at the top box you put NH3. Now actually we've already looked at the Lewis structure of NH3 in class. Okay, so, but we're going to be drawing it here, going through these steps. So we have to come up with our pot of valence electrons. So in that one box, however you want to do it, come up with a pot of valence electrons. I took 1 times 5 electrons because nitrogen, there's only one atom, and nitrogen is a 5A element. So 1 times 5 electrons is 5 electrons. Hydrogen, 3 times 1 electron is 3 electrons. So the total is 8 electrons. Okay, so that goes in the first box. Then if you go down to the next box, we're ready to go ahead and arrange this thing. So I think I told you hydrogen never wants to be in the middle. So we're going to put nitrogen in the middle, just like you've probably seen it before in other structures of ammonia. Nitrogen in the middle, and sigma bond to 3 hydrogens. So that will be in the box underneath. So like in lecture, what we did then is we compared the number of electrons that we had used up with how many we had in our pot. And so when you do that, actually, you had 8 electrons in your pot. You used up 6. I know it's hard to read, but you used up 6 electrons. 6 electrons came from 2, 4, 6 electrons. So we have 2 electrons to distribute. Okay, and then we're to step number 4. So those 2 electrons need to show up on our Lewis structure. Usually you take these extra electrons and put them around your outside or terminal atoms, but hydrogen doesn't want any more electrons. So we're going to turn to our central atom, who only has 6 electrons, and that's where those 2 electrons are going to go. Okay, so we redraw our structure in the box underneath. Nitrogen, single bond hydrogen, single bond hydrogen, single bond hydrogen, and then also on the nitrogen, we're going to go ahead and put those 2 extra electrons right there. Now step number 5 doesn't always apply, and actually step number 5 doesn't apply here either. Step number 5 is you turn your attention to the middle atom, which in this case is nitrogen, and if it doesn't have a complete octet, then you need to swing some lone pair electrons in, make a pi bond. So we're done. So So we're ready for our checks. The first check is the total number of electrons in this final Lewis structure. Is it the same as our pot? And yes. Okay, do you buy that we have 8 electrons shown there, and our pot was 8 electrons? So that's cool. Do each of the atoms, the nitrogen atom and the 3 hydrogen atoms, do they have a rare gas configuration? Yes, they do. So that's a good check there. Since this is a neutral molecule, okay, we talked about the expected rules of valence, or expected valence of the atoms. So just to kind of remind you how that goes, yeah. I'll just put group, let's see, starting with 4A, 5A, 6A, 7A, okay? The expected valence, and just to remind you what that means, that is the number of sigma and pi bonds. Okay, so it's always 8 minus the group number. So 8 minus 4 is 4, 8 minus 5 is 3, 8 minus 6 is 2, 8 minus 7 is 1. So nitrogen is a 5A element, so we expect it to reach out 3 times. That's all I'm saying. So is nitrogen reaching out 3 times? Yes. The expected valence of hydrogen is 1. And do you remember what the expected valence of boron is? Our trouble guy? Yep, 3, exactly. So that's all we mean. So yep, that works. Okay. All right, so the last thing in the column for each of the ones we do is with regard to hybridization. Now, remember that hybridization and structural geometry, these questions, only apply to a particular atom, not the whole molecule. So we're going to pick the middle atom. And sometimes if there's only 2 atoms, I'll tell you which one we're going to pick. So of course, these are questions about nitrogen. And we said that, well, I'm not going to redraw it here. In your background information for today's lab, you have that table that had kind of the 3 rows. Okay, good. You had a row that said 2, and 2 meaning sigma bonds and lone pair electrons. And then you had a row that said 3. And then you had a row that said 4. Okay? So can you see with regard to the nitrogen atom, the number of sigma bonds, I know it looks messy up there, but the number of sigma bonds, 3. The number of lone pair electrons, 1. So 3 plus 1 is 4. So we're at that bottom row. Okay? So that's why here I've gone ahead and that corresponds to sp3 orbital hybridization. And these other 2 things come right after that with regard to nitrogen. The structural geometry is tetrahedral, and the bond angle is 109.5. So that's how you do ammonia. Okay? Now, one other thing that you guys are going to be doing, and I'll just pass them out, is you guys are going to be making these structures. Okay, out of, oops, I'll get it. Oh, you can get it. Making these structures, thanks. Now, color, if you've done much with these, actually they are color-coded, but we're not going to follow the colors, okay? I just want you to, thank you again. They're terrible to pick up. I just want you to just make the ammonia molecule. Thank you very much. Yep. And don't forget the lone pair electrons. So I've got extra ones of these. So this one was extra full. I'm not too sure. So I'll put it here. So between the 2 of you, go ahead and make that molecule. And you can make your own or work together, but my favorite is for all these central atoms to always pick a black one. I know that's usually carbon, but if you pick a black one, then things kind of fall into place. I won't belabor these as much as I belabored this one. Hopefully I'll push the right buttons here. All right. So the next one, it's first going to go ahead and write all this stuff. Let's see if I can speed that up. I should be able to. Okay. So this one, drum roll please. We are going to do the formula H2CO. H2CO. So that goes at the top. So you can go ahead and do the first box, which is how many, what's the pot of electrons brought by those, 4 atoms? And this is where I see Mitchell's got his periodic table handy. That is very handy. You probably will need a periodic table to do Lewis structures, I think. So 2 electrons, 2 times 1 electron for hydrogen, there's 2. 1 times 4 electrons for carbon, that's 4. 1 times 6 electrons for oxygen, that's 6, for a total of 12. Okay, so for the box underneath that, we're ready to go ahead and come up with our preliminary Lewis structure. So your choices are putting hydrogen, carbon, or oxygen in the middle. Remember, hydrogen never wants to be in the middle, okay? Carbon and oxygen. So if you find them on the periodic table, they actually happen to be in the same period. Okay? So remember that the one to the left is the lower electronegativity, and that actually, according to your rules of drawing Lewis structures, the lower electronegative atom wants to be in the center. So then the box underneath that we can go ahead and draw our preliminary Lewis structure that looks like this. It has a central carbon atom, single bonded to each hydrogens, and also single bonded to the oxygen. So before we go on to the next step, we need to see how many electrons we have left over. So we had a pot of 12 electrons. We've used 6 in this preliminary structure. So 12 minus 6, we have 6 electrons to what we say distribute around the Lewis structure, whoever needs them. And this is where I told you, or your general rule is to make sure that the outside atoms are happy first. And so hydrogen doesn't want any more electrons, but oxygen sure heck does. It only has 2 electrons now. Actually, it's going to use all 6 of those. So we're going to have 3 pairs of lone pair electrons around that oxygen. So we'll go ahead and draw that next Lewis structure. So we have the single carbon atom, central carbon atom, singly bonded to 2 hydrogens, also singly bonded to an oxygen with 3 pairs of lone pair electrons around that oxygen. So now actually the 5th step does apply, because the 5th step usually has to do with the central atom. The central atom right now only has 6 electrons. So we can give it 8 if we swing, and you can choose whichever one you want to, 1 pair of lone pair electrons in. Okay, and I chose the north one. It really doesn't matter. So then when we do that, our final Lewis structure looks like this, where again we have the carbon in the middle, singly bonded to 2 hydrogens, and now doubly bonded to an oxygen with 2 lone pair electrons around its outside. So that looks pretty good. Let's do our checks. Hopefully, if we count the number of electrons in our final Lewis structure, it is 12. Okay, 2, 4, 6, 8, 10, 12. Looks good to me. Each of the atoms actually does have a rare gas configuration, okay, by those, the carbon and the oxygen atom actually sharing 4 electrons. That works for both of them. They each have a complete octet. Since this is a neutral atom, we expect it to follow the valence rules. Carbon is, you find it under 4A, so 8 minus 4, it reaches out 4 times, and it is reaching out 4 times. Oxygen is at 6A, so 8 minus 6 is 2. The oxygen is reaching out twice here. Hydrogen is reaching out once. So yep, it is actually this structure. Now they don't always follow the expected valence rules. So with regard to hybridization and all of these questions, we're going to turn our attention to the carbon atom. So how many sigma bonds extending from the carbon atom? I got 3, yep. How many lone pair electrons? None from the carbon. Okay, so we're at that middle row, aren't we? So it's sp2 orbital hybridization, and then the other things fall into place. Of course, that means the structural geometry is trigonal planar, and the bond angle is 120 degrees. Make that structure. So now, on to the next one. Looking good. Speed up. Bop. Drum roll. So we have that hypochlorite polyatomic anion. It's only 2 atoms, runs around with -1 charge, so ClO, -1. So your pot of valence electrons, it will be 1 chlorine times 7 electrons for chlorine, 1 oxygen atom times 6 electrons, so 6 electrons. The fact that it's got a -1 charge, you have to kick in 1 electron. So if you add that all together, we're looking at a pot of electrons to distribute around our Lewis structure of 14 electrons. So the next stage is kind of funny. You draw the preliminary Lewis structure, deciding who you're going to put in the center. And so it looks like this. Cl sigma bond O. That's our preliminary Lewis structure. And just for kicks, I'm going to go ahead and say the central atom is the oxygen atom, just so we can kind of finish the exercise, okay? So with that in mind, let's see. We have to see how many electrons we have left over. So we started with 14. There's only 2 shown there, okay? So 14 minus 2, we've got 12 electrons that we can distribute around this preliminary Lewis structure. And if you look at it, my goodness, it looks like both atoms, they want 6. So that's going to be fine. Okay, so, I mean, they only have 2. They're sharing 2, and they need 8, so both of them need 6 apiece. So we're going to redraw the chlorine and the oxygen, and we're going to distribute 6 electrons in pairs. So 3 pairs around the chlorine, 3 pairs around the oxygen. And that's looking pretty good. Okay, so, all right. Now, remember I said in lecture that if you have an ion, negatively charged or positively charged, you're drawing the Lewis structure, you have to put the whole thing in brackets and put the charge outside. So I've gone ahead and done that here. Actually, with regard to the last step, oxygen has a complete octet, so that last step is not applicable. So we're done. We are totally done. That seems kind of strange, but let's do our checks. So do you buy that we actually have 14 electrons in our pot? And we do have 14 electrons, 2, 4, 6, 8, 10, 12, 14. We do have 14 electrons in our final Lewis structure, so that check is great. Do they both have a rare gas configuration? Yep, they do. They both have a complete octet. Since it's not a neutral molecule, that last check is out the door. And I think I might have done this in class, but do you see where, let's see, we said oxygen is a 6A element, so 8 minus 6 is 2. You expect it to reach out twice, and it's only reaching out once, so Chlorine is a 7A, so 8 minus 7 is 1, so chlorine is following expected rules of valence. So this is where I said we're going with the oxygen as the central atom, which, all right, so around the oxygen atom, how many sigma bonds? 1. And how many pairs of lone pair electrons? A whopping 3. Is that wild or what? So we're back to that third row, right? Okay, so it's sp3 orbital hybridized. That comes along with the geometry, the structural geometry around that atom is tetrahedral. The bond angle is not applicable. To have a bond angle, you need to have basically it connected to 2 atoms, okay? So the bond angle is not applicable. Okay, so go ahead and make that structure. Fast forward. Drum roll. Okay, so what is the most abundant gas in this room right now? Astronomy people?
Like that we breathe?
That we breathe.
Nitrogen?
Nitrogen. Yep, exactly. That's what we're going to do next. Perfect. Nitrogen.
That's like another question.
So we're doing nitrogen, N2. And so the pot of valence electrons isn't too bad to come up with. We just take 2 times how many valence electrons one of them has, which is 5. So we have a pot of 10 electrons to distribute around those 2 cute little atoms. So in the next box, go ahead and draw the preliminary Lewis structure. Nitrogen, sigma bond nitrogen. You're like, all right then. So we've used 2 electrons, and we have 10 electrons in our pot. Okay, so the leftover electrons are 8. And kind of like we laid it out before, if you don't mind, let's go ahead and go with the central nitrogen atom is this right one, and the outside one is the left one, just kind of for purposes of who do we satisfy first. Oh my goodness, so they both have an issue, right? They both need 6 more electrons, right? But my, algorithm to coming up with the correct Lewis structure is I would go ahead and satisfy one of them first. So actually, I'm going to put 6 electrons around the terminal nitrogen, okay, and then the other 2 around the central nitrogen, okay? So my preliminary Lewis structure looks like this. On the left nitrogen, I have 3 pairs of lone pair electrons, sigma bond nitrogen, and then on that right nitrogen, I have 1 pair of lone pair electrons. So I did my budget, okay? So now step number 5 does apply, because if we go ahead and we say the right nitrogen is our central atom, it's only got 4 electrons, and it needs 4 more. So this is an example where actually we are going to swing 2 pairs. We're going to swing 2 pairs of lone pair electrons in from our terminal nitrogen. Okay? So if we redraw this structure in the 5th box, it looks like this, where we have the nitrogen now on the left has only 1 pair of lone pair electrons. We have a triple bond between the 2 nitrogens, and then the other nitrogen still has the lone pair electrons it had in the first place. So if we do a check, we should actually have 10 electrons around the final Lewis structure. 2, 4, 6, 8, 10. So that check is right. The next check is, do each of them have a rare gas configuration? And the answer is yes. They share 6 electrons between them, and they each have 2 of their own. So 6 plus 2, they each have 8 electrons. And nitrogen is a neutral molecule, so does it follow the expected valence rules? And actually nitrogen is a 5A, so 8 minus 5 is 3. So it is reaching out 3 times. So that's correct too. So it's very symmetrical, obviously. So we could point to either one of these atoms, but let's go ahead and point to the right atom over here. So how many sigma bonds is that nitrogen atom reaching out? Just once, exactly. How many pairs of lone pair electrons? Just 1. So 1 plus 1 is 2. So you're back to that top row, okay? And the top row is sp, orbital hybridization. Okay, and of course that's associated with linear shape or structural geometry. And the bond angle is not applicable again here, okay, because there's not 2 atoms it's stuck to. So go ahead and make that atom, or make that molecule, excuse me. Part of your ticket out of here, I guess. Okay. So here's a list of 6, and I'll go ahead and leave this up here for a little bit, but what you might want to do is go ahead and take 6 columns. In the top box, write H2O, O2, SO4 2 minus, Cl2CO, HCN, and NO2 plus. Okay, so those are your 6 that you need to do, and I need to take a look at your worksheets before you do that. What? Oh. It's always something. Let's see. I'll write them over here. How's that? Okay. Because I'm not sure what I need to do to get that back. I promise I'm not like taking my stupid pill or anything.